being recorded. So, good afternoon, everyone. Welcome to the CFTC webinar. Today is a pleasure to welcome Haroldo Ribeiro from Universidade Estadual de Maringá, no Brasil. Haroldo did his PhD in Universidade Federal de Maringá, where he also did his master and bachelor degrees. Now Haroldo is an assistant professor in the same university, but before he did a few appointments, for instance, in the Northwestern University in 2012, and he was an assistant professor in Universidade Tecnológica Federal do Paraná, right? And today he kindly agreed to present his work on machine learning applied to liquid crystals. But before I hand over to Haroldo, I'd like to say a few announcements. First, that the seminar is being recorded, so by staying, you agree to have your voice and image recorded. And second, please turn off your camera and microphone, except the speaker, of course, for stability reasons. So, Haroldo, the floor is yours. Thank you.
Thank you, Rodrigo. So I will share my screen. So let me see if this experiment works. So let's try. Okay, so it seems to be working, I guess. So I'll be putting full screen. So I think that everybody is seeing. Can you confirm?
Yeah, perfect.
Okay, so thank you all for coming to this talk, for joining this talk, actually. And before I start, I wish to say thank you to Rodrigo and also to Professor Paulo for the invitation, and also for Igor Piaget for kindly suggesting my name to this seminar series. Okay, so I will be talking about using ordinal methods and simple machine learning to predict properties of liquid crystals from images of these materials. And okay, so maybe to motivate this, I would say that we are now seeing a surge of applications of machine learning methods in different disciplines and areas. And this is not different in physical science and in physics in particular, and also in material science. And I think that perhaps we can say that this surge of applications is explained by the availability of large data sets, and also because implementing this machine learning is now quite simple. So we have many computational implementations for using these approaches. And some people consider this surge of applications of machine learning as a fourth paradigm of science in material science. However, not all areas are taking advantage of using this approach for investigating I don't know, properties of materials, for instance, and that's the case of liquid crystals, where we do not see many works using machine learning to investigate properties of these materials. And this is kind of surprising because liquid crystals are often studied using image techniques, for instance, the polarized microscope imaging technique. And it is exactly with image that machine learning has achieved great success in recent times. And the outline of this talk will be to present two recent works that try to reduce the shortage of studies using machine learning to investigate properties of liquid crystals. And I divided this talk in two parts. In the first part, I will be talking about using the complexity entropy plane to predict properties of liquid crystals. And this part is basically related to this PRE that we published some time ago. And we will be using simulated textures, so texture generated from simulations. And in the second part of the work, I will be talking about using ordinal networks. That is another ordinal method that is closely related to the complexity entropy plane. And in this case, we'll be using experimental textures obtained from real samples of liquid crystals. And this other part is related to a work in progress that I hope will be published next year. Okay, so to start, I need first to present to you the band-point symbolization method that is the core of the complex entropy plane and also the core of the ordinal networks. And this approach was actually proposed as a tool for analyzing time series, actually for defining a complexity measure for time series. And only later we generalize this to be used with image. So I will start from the beginnings, from presenting this approach for time series. And I think that's more easy to describe this approach with a simple example. So suppose we have this time series here. So a time series with elements 4, 9, 7, and so on. And the first step of the approach is to define a sliding window of a given size. So in this case, I'm using a sliding window of size 3. And the size of the sliding window is what we call embedding dimension. And the idea is to select the elements inside the sliding window and determine what is the permutation of these elements that sort the values in ascending order. So we can do this by using some index numbers, like these ones that I'm associating with the values in this partition. And then we sort the values in the partition in ascending order, and we apply the same permutation to the index numbers. And this defines the ordinal pattern or the permutation symbol associated with this part of the time series. And what we do next, we move our sliding window one step ahead, and again we get the new elements. So in this case it's 9, 7, 3, and because they appear in decreasing order, we already see that the order of the permutation symbol that sort these numbers in ascending order is 2, 1, 0. And then we keep doing this up to the end, up to the last position of our sliding window. And by the end, what we end up having is a map between a time series and a symbolic sequence. So we map this time series into this symbolic sequence where each of these symbols are associated with the order of the time series in the sliding windows that we use it to define this. But so Bunnypump proposed this approach, but not only this. Actually, what they proposed was to estimate a probability distribution associated with these ordinal symbols or these ordinal patterns. And we can do this just by counting the occurrences of each of these symbols. So in this case, because we are using a partition of size 3, we have actually 3 factorial or 6 possible ordinal patterns. And just by counting the occurrence of each one, we can define the ordinal probability distribution. So for instance, in this case, the ascending permutation, the 0, 1, 2 occurs twice. So we have a probability that's 2 in 5. And by doing so, we can estimate all the others probability for each of the ordinal patterns. And using the ordinal probability distribution, the Bunnypump actually proposed a measure that we call the permutation entropy, that is basically this part of the expression I'm showing here. And this is just the Shannon entropy of the probability of the ordinal probability distribution. And what I will be actually using is not just the Shannon entropy, but is the normalized Shannon entropy or the normalized permutation entropy, that is basically the permutation entropy divided by its maximum value that I'm calling S max. And as you know, the Shannon entropy is maximized when all probabilities are the same, when we have a uniform probability distribution. And in this case, the S max will be the log of the number of states. So in this case, I will be dividing by log of 6, but in more general, we can divide by the log of the embedding dimension factorial, as I am showing here. Okay, but this is for time series, and we need an approach to estimate the complexity or to estimate the property of images of liquid crystals. And we actually generalized this approach to two-dimensional data such as image some time ago. And it's actually quite simple. So suppose we have, again, an example. So in this case, we have a 3x3 image where the values represent the pixels intensity. So in this case, 1, 2, 1 are the pixels of this hypothetical image of size 3x3. And to generalize this, we can just, instead of using a one-dimensional sliding window, we can now define a two-dimensional box that I'm showing you by these green dashed lines. So we have an embedding dimension in the horizontal direction that I'm calling dx, and we also have another embedding dimension in the vertical direction. And what we do is basically the same. So we get the values inside the sliding box. So in this case, it's in the first position of the sliding box, we get the values 1, 2, 8, 3. And After that, we flatten this 2x2 matrix into a simple array, so a one-dimensional array. So in this case, I'm flattening line by line. So we have 1, 2, 8, 3. And from here, it's basically the same. So we sort the values in ascending order, and then we apply the same permutation to the index numbers. And then we get our permutation symbol or our ordinal pattern associated with this part of the image. And then we move our sliding box one step to the left, and we get the new values, and we repeat the process. So we get the values, we flatten, then we sort, and then we estimate the permutation entropy or the ordinal pattern of that part of the matrix. And we keep doing this up to the end. And by the end, we have basically the same. So we now have a map between a two-dimensional array or a matrix or an image and an array of possible or an array of permutation symbols. So in this case, there are 3 different symbols here. And again, we can calculate the probability of finding each of these possible symbols just by counting the occurrence of each one. So in this particular example, we have only 3 that occurs. All the others have probability 0. And again, using the ordinal probability distribution, we can estimate the normalized permutation entropy in the same way. So in this particular case, because we are using a sliding box with 4 elements, we have now 4 factorial or 24 ordinal patterns. And our S max in this case is also generalized to this expression. So instead of having just the log of the embedding dimension, we now have the log of the product between the 2 embedding dimensions factorial. Okay, and for both time series and image, I think that we can say that the normalized permutation entropy is measuring the degree of disorder in our system. So for instance, if we have a time series that is monotonically increased or a very regular time series, we will probably find one ordinal pattern with high probability, and all the others will have low probability. And in this case, if we calculate the normalized permutation entropy, we end up having a low value for the permutation entropy. And this is basically the same if we have a very regular image, for instance, just a blue image. Again, we will find just one probability, just one ordinal pattern, and all the others will have probability 0, and then we have a permutation entropy that is equal to 0. So order resistance will be characterized by low permutation entropy. And in the other extreme, if you have a very disorder resistant, so for instance, a random time series or a very noisy image, we expect to find all ordinal patterns with the same probability. So in this case, our ordinal probability distribution will be very close to a uniform distribution. And in this case, the channel entropy will be very close to its maximum value. So we expect to have high entropy in this disorder resistance. And in between these 2 cases, we can have a lot of different types of systems that have some intermediate degree of order. Okay, but perhaps you may agree with me that only the entropy is not enough for capturing our intuitive idea of complexity. And I say that because if you consider the 2 extreme cases, so a system that is very ordered and a system that is very disordered. So in these 2 cases, we think that we can consider they simple because we just need one probability to describe the system. So in the case of the very ordered system, there is only one state that occurs. And in the other extremes of a very disordered system, we just need also one probability because all probabilities are the same. So the system is close to a uniform distribution. So perhaps we can agree that these 2 systems are equally simple. And what we may consider as a complex system is somehow in between these 2 extremes. So in between the ordered system and the disordered system is what we may agree to call a complex system. So if entropy is not enough for capturing this intuitive idea of complexity, what we can do? And one thing that we can do is to estimate another quantity that we call a statistical measure of complexity that has been defined in these physics letters A by Lopez Ruiz and his collaborators, and also by Haroldo and his collaborators in these physical review letters. And basically, to define this quantity, we need first to define a disequilibrium measure. So this is what I'm showing here. And suppose we have now a probability distribution P that represents our ordinal probability distribution, and then we have a uniform distribution. And what the disequilibrium is basically a Jensen-Shannon divergence normalized. So we have here the Jensen-Shannon divergence, and this is just a normalization constant. So this is our disequilibrium. So it's a measure that calculates something between the probability distribution of our system and the uniform distribution. And actually, the values of D is quite similar to a distance. It can be considered a distance, a metric, in a sense that if we have a system that is very disordered, so a system with probability very close to the uniform distribution, the disequilibrium will be zero. So the distance between the probability and the uniform distribution will be zero because the system's probability is approaching the uniform distribution. And in the other extreme, if we have a very ordered system where we have only one probability and all the others are zero, so the disequilibrium will be maximum. And because we are normalizing here, we have a disequilibrium equals to 1 in this case of a very ordered system. And what we define as a statistical measure of complexity is actually the product between the disequilibrium and the normalized entropy, exactly as I am showing here. And to have a more clear idea of this quantity, perhaps we can make some plots. And what I'm showing here is just a plot of entropy as a function of the degree of disorder in the system. So as we already have seen, if we have a system that is very ordered, its entropy will be low. And as we increase the degree of disorder, the entropy will increase. And the disequilibrium works, when the disequilibrium goes in the opposite direction. So if we have a very ordered system, the probability distribution of the system is very far from the uniform, so the disequilibrium will be large. And as we increase the degree of disorder, the system's probability approach the uniform distribution and the disequilibrium goes down. And because we define our complexity measure as the product between these two quantities, a graph of the complexity as a function of the degree of the disorder in the system will be somehow like this one. So we have a maximum in between these two extremes of order and disorder, and these somehow agree with this intuitive idea that complexity is in between a very ordered state and a very disordered state. But what we will actually use is these two quantities. We will estimate the values of entropy and the values of complexity from our images of liquid crystals. And this builds up what we may call a complexity entropy plane. So it's basically, we can consider this as a map where we map the image or a time series into a point in this complexity entropy plane. And using these two values, we will be characterizing our system. So again, if we have a very ordered system, our entropy will be low, and also our complexity will be low. So we will be somehow localized in this region of the complexity entropy plane. And if we have, on the other extreme, if you have a very disordered system, a very random system, we will have a system with entropy high, but its complexity will be also low, and in more general, will be localized in this region of the complexity entropy plane. And complex systems may be somehow localized in this region. And I need to say also that for a given value of entropy, there is a range of possible values for complexity, in a sense that the complexity is not a trivial function of the entropy. And this defines a region of possible values in the complexity entropy plane. That is more or less what I'm trying to show here by these dashed lines. Okay, so just to illustrate a bit more with a few examples, so consider some time series first. So I'm showing here some time series of the fractional Brownian motion. And this fractional Brownian motion has one parameter, that is the Hurst exponent. And the Hurst exponent somehow controls the roughness of the time series, in a sense that if we have small values for the Hurst exponents, we end up having a very rough time series such as this one. And as we increase the Hurst exponent, we end up having smoother and smoother time series such as this one that has a very clear increasing trend. And so if you have this time series and then we apply our band pump symbolization method calculate our ordinal probability distributions, and from this probability, we estimate the values of complexity and entropy, we'll be mapping each of these time series into a point in the complexity entropy plane. And that's exactly what I'm trying to show here. So again, if you have, I think that these somehow agree with our idea of complexity in a sense that this is more random than this. So we have a point that time series with a small value of the Hertz exponent is localized in this region of the complexity entropy plane, where if we have a smoother time series, it will be localized in another region that has low entropy and high complexity. But okay, this is for image. And what about this is for time series. And what about for image? That's what I'm trying to show here. So again, we have some fractional Brownell motion surfaces or fractal surfaces that are again characterized by a parameter, the Hertz exponent. And again, if you have small values of the Hertz exponent, we generate very rough time series. And as we increase the values of the Hertz exponent, we get smoother and smoother time series such as this one. Okay, so suppose we have this image and then we estimate our complexity entropy plane. Actually, we apply the band pump symbolization approach, estimate the ordinal probability distribution, and from the ordinal probability distribution, we can estimate the values of complexity and entropy. So each image will be mapped into a point in the complexity entropy plane. And again, I think that this somehow agree with our intuitive idea of complexity and entropy in a sense that very rough images are localized in a region of the complexity entropy plane characterized by high values of entropy and low values of complexity, while smoother time series will be localized in another region that has high entropy, that has low entropy and high complexity. And just to give a final example of this, we actually applied the complexity entropy plane to investigate art painting. So this is just a simple example where we actually obtaining a lot of images from art paintings, and we estimate the values of entropy and complexity for each one. And after that, we average the values inside some time window. So that's exactly what I'm showing here. And this basically shows the evolution of art paintings in the complexity entropy plane. And the localization of the points in the complexity entropy plane somehow match with the art periods. For instance, we have these points here are usually associated with modern art, and after modern art ends, we see a transition to the postmodern art that is also captured by the values of entropy and complexity. So the transition from this to this part of the complexity entropy plane. Okay, but we need to get back to liquid crystals because that's the point. My presentation is about liquid crystals. So as I told you before, I will be first describing some results related to simulations. And what I'm showing here is some textures obtained from Monte Carlo simulations of a model that describes liquid crystals. So this is simulated textures. And this model has two phases. So it is in a nematic phase if the temperature is smaller than this critical value. So 1.1074. So this is the critical temperature. So simulations or textures generated with temperatures below these values will be in the nematic phase. And if you are above this temperature, we'll be generating textures from the isotropic phase. And basically, this point is showing the transition. So from here, we have isotropic textures, and from here we have nematic textures. And each of these textures actually have another parameter associated with them. So in this case, I don't know, maybe it's some value close to 1, and in this other extreme, so temperature that's 0.9, we will have a low value of the order parameter. But if you look careful into this texture, it's very hard to visually differentiate this texture. So they are actually quite similar, and just by looking, it's probably very hard to see that they are different. But our idea is now to use the values of complexity entropy to try to predict the values of the order parameter using simple machine learning. And to kind of see if that works, we first estimate the values of entropy and complexity as a function of the temperature. And that's exactly what I'm showing here by these two plots. So as you can see, the values of entropy captures the evolution of the system with the temperature. So even if the textures are quite similar, we can have values of entropy and complexity that are capable of distinguishing between two textures with different temperatures in the nematic phase. And we also see that these two quantities are capable of identifying the phase transition. So we have a peak in the complexity exactly at the temperature that the system is transitioning from the isotropic to the nematic to the isotropic phase, and this, we have a similar behavior for the entropy. So basically, this indicates that our approach can work. So our values of entropy and complexity perhaps can predict the order parameter of the system directly from their images. And so we try to do that. So we have now the values of entropy and complexity. And we also have the values of the order parameters. And what we did actually was to train one of the simplest machine learning approach, so that is the k nearest neighbor, or the KNN, with a sample of values, a sample of textures that we know the values of the order parameter. So we have these training sets where we know the values of the order parameter, and then we estimate also the values of entropy and complexity. And I will actually show how the KNN works, but it's quite simple. It's actually one of the simplest machine learning algorithms. And so it works more or less like this. So it actually, we can say that the KNN is just remembering our data set. So suppose we have these points here that represent textures with a given value of the order parameter. So each point has a value of P attached to it. And we also have the values of entropy and complexity. And basically what the KNN will do is just to remember the position of the training set. And so now suppose we have a new texture, a texture that we never exposed to our algorithm, but we can still estimate the values of complexity and entropy. So we can map this new image into a point in the complexity entropy plane. And then we can ask, what is the order parameter of this new texture? And the answer that KNN provides us is the following. So you look into the neighborhood of this new point, and you estimate the average values of the order parameter in the neighborhood of this new point. And this will be our estimate for the order parameter of the new image. And basically that's it. That's all we need to know about the KNN to proceed. And so we did that. So we trained our KNN model with a lot of texture, a lot of simulated textures. And then we generate new textures where we, in principle, do not know the values of the order parameter. And then but we can still estimate the values of entropy and complexity and use these values as an input to our KNN model. And the KNN model will return the values of the order parameter. And as you may guess, there is only one parameter in this KNN algorithm, that is the number of neighbors. And we can estimate an optimal value for the number of neighbors using the training set. So we can divide the training set into two sets again. So we have now the training and the validation sets. And for that, we can estimate, in this case, I'm estimating the coefficient of determination between the true and the predicted values in the training set. And by doing so, we can find a best value, an optimal value for the number of neighbors. I think that we have used something around 20 in this case. And what I'm showing in this box here is actually an example of prediction. So we generate a lot of new textures that were never exposed to the algorithm. And we map the values, and then we use the KNN to find the values of P. And these blue squares here show an example of predictions. And as you can see, it's not perfectly. We have some noise. In particular, we have large noise around the critical transition. But I think that we can say that this approach works quite well, because the true and the predicted values of the order parameter are somehow close. And because that works, we actually try another thing. So we generate now textures of liquid crystals in the cholesteric phase. And this cholesteric phase is characterized by a parameter that is the pitch, that I think that we can perhaps say it's just a period in the molecular orientation of the material. more or less what I'm trying to show here. So in this case, we generate textures with 9 possible pits of these values here. So 15 nanometer, 17, and so on, up to 40 nanometer. And what I am showing here is 5 examples. So five textures that were mapped, 5 textures for each of these cholesteric pits that were mapped into the complexity entropy plane. And this actually shows a few textures, 3 textures for a few values of the pits. And what we see here is that more or less each pit is somehow localized in a region of the complexity entropy plane. So this indicates that these 2 values can be helpful in predicting the pits of this material. And well, it probably will not perfect. As you can see, we have a lot of overlap in between some values, but it has some potential. So we try to do that. So we generate some textures of this and we train a KNN model. But this time, instead of having a regression problem where our KNN model will output a real value, so in this case, our KNN model will just say if our textures belong to one of these 9 class of pits. And so for doing so, we can still use the KN, but now the KNN for classification. And it's actually even simpler than the case of regression. So suppose we have now this training set. So each color of this point represents a pit associated with an image. And then this is our training set. So we remember this point and we generate a new instance with a given pit, and we estimate the values of entropy and complexity. And so this new texture will be mapped into a position in the complexity entropy plane again. And now we ask, what is the pit of this new value? And what the KNN will answer this time is look into the neighborhood and find what is the most common pit in the neighborhood. And the most common pit in the neighborhood will be our prediction for the pit of this new image. So it's basically the same, but now we have discrete classes, so a discrete number of possible values. And we did that. So we estimate, we train our KNN model, and then we estimate the confusion matrix that in this case, sorry, I need to say that we also optimize the number of neighbors, more or less that's what I am showing here. And to verify the quality of these predictions, we estimate now the confusion matrix associated with the predictions in the test set. So in the set of textures that were never exposed to the algorithm. And this is basically what I am trying to show here. And I think that we can read, it's easy to read this matrix, this confusion matrix, perhaps line by line. So if we have a perfect classification, so the confusion matrix will be just diagonal with all elements equals to 1. And I think that we can read this in this following. So suppose we have a image that, or a set of images that have 15 nanometers of pit. Our approach always say that this image that has 15 nanometers is actually 15. So in this case, we are never wrong. But as you increase the pit values, you can see that the approach doesn't work so good. So for instance, in this case where we have 23, a texture or a cholesteric phase, a cholesteric texture with 23 nanometers of pit, you see that our approach predict that it will be 23 in 74% of the time, but it also predict that it can be 21 nanometers in 21% of the time. It can also say that this texture has a 15 nanometers of pit, but it's very rare. But even so, it's not perfect, but it's somehow good. So as you can see, we have the largest values in the diagonal of this confusion matrix. And more than that, you also see that when the method make a wrong prediction, it tends to predict a value that is close to the real value. So it's a good feature of this model. Okay, and basically that's what I have to say about using the complexity entropy plane. And I will be now moving to the second part where we will now use the ordinal networks. And well, first I need to say what an ordinal network is. And again, similar to what happens with the permutation entropy, ordinal networks were also proposed to investigate time series, actually to be a map between time series and complex networks. And the idea is that we map a time series into a complex network and use the properties of the network to characterize the time series. And there is not only the ordinal network, so there are many other approaches that map time series into complex networks. But in this case, I will be talking just about the ordinal networks. And what is the ordinal network? So basically, it's a representation for the symbolic sequence that we obtain after applying the bump pump symbolization method. And in this representation, the nodes of the ordinal network will be the permutations or the ordinal patterns that appear in the symbolic sequence. So in our previous examples, we find these ordinal symbols or these permutation symbols, and we have 4 different symbols. So the ordinal network representation associated with this symbolic sequence will be a network with 4 nodes, exactly these ones that I am showing here. And in addition to the nodes, we have the connections. So in the connections reflect the transitions between ordinal patterns in the symbolic sequence. So we see a connection between the permutation 021 and the 210 because we have this transition. So a transition from the 021 to the 210 in the symbolic sequence translates into an edge in our ordinal network. And if we find another transition of this type, this edge will be weighted twice. So in addition, sorry, I forgot to say that the ordinal network is also directed, and the direction of the edge corresponds to the direction of the time in this case. So that's why we have a connection from this node to this node. And in addition to be directed, these transitions or these edges are also weighted by the number of times we find this particular transition in the symbolic sequence. Okay, but this is for time series, and we need the ordinal networks mapped from image. But as you may guess, it's more or less the same. So instead of now having a symbolic sequence, we have a symbolic array, and we now consider transitions in the horizontal and in the vertical direction. And this will again create a network representation for the image, and we can use the image to characterize you actually can use the network to characterize the image. And to illustrate, so let's once again use the fractional Brownian motion. So in this case, I'm using fractional Brownian motion time series. So these are some examples, some samples of this process and their corresponding ordinal networks representation. And as you can see, so the ordinal network somehow captures features that we see in the time series. For instance, in this case, we have a very clear downward trend for this particular value of the Hertz exponent in this particular realization of the fractional Brownian motion. And that translates into a very strong auto loop in the permutation 210, because the permutation 210, it's exactly associated with the downward trend. So we have a lot of 210 followed by 210 in our symbolic in our symbolic array associated with this time series. And so we can just look into the network, but we can also estimate some properties of the network. So in this case, I'm just estimating one of the possible properties that we can use. There are a lot. In this case, I'm estimating the average weighted shortest path as a function of the Hertz exponent. And as you can see, we have more or less a 101 relationship between the average shortest path and the Hertz exponent. And this indicates that we can use the average shortest path to predict the Hertz exponent of our time series. And when we go to fractional Brownian motion surfaces, it works more or less the same. So in this case, I'm actually using a sliding box of 2 by 2, and that translates into an ordinal network that has 24 nodes and a lot of connections. And again, you can see that just the visualization of the ordinal network already says something about our fractional Brownian motion. So we clearly see some change in the connectivity patterns of our ordinal networks. but we can again estimate some quantity, some metric of these ordinal networks. And what I did was to estimate again the averaged shortest path for each of these images. And you see here basically the same plot. So again, we can use the average shortest path as an indication of the Hertz exponent associated with the values of the fractional Brownian motion surfaces. Okay, but we need to get back to liquid crystals one more time. And in this case, as I told you before, we will be talking about experimental textures, and experimental textures obtained from samples of these two liquid crystals, so the 8CB and the E7 liquid crystals. And these two materials, we also doped with two chiral dopants. So these two compounds here, the R811 and the S811. And what I'm trying to show here, it's more or less a phase diagram of this liquid crystal. So when we have a pure 80CB sample in a low temperature, it will be in a SMACTA phase. And as we increase the temperature, the system undergoes a second order transition to a nematic phase. And if we keep increasing, we find a first order transition to the isotropic phase. And if we dope these 80CB samples with the R811 or the S811, we modify the phase in a sense that for low temperatures, we now have the chiral SMACTA phase. And as we increase the temperature, we again see a second order transition now to the cholesteric phase. And if we keep increasing, we find a first order transition to the isotropic phase. And for the E7 samples, things are more simple because we just have two phases. So in the case of the pure E7 samples at low temperature, the mesophase is a nematic phase. And if we increase the temperature, we see a first order transition to the isotropic phase. And in case of doped E7 samples, the phase for low temperature is a cholesteric phase. And as we increase the temperature, we find an isotropic transition to the isotropic phase. And for the E7 samples, we actually produce two groups of samples. So in group one, we only doped our samples with a given percentage of R811. And in group two, we did a racemic mixture of R and S811 in a sense that we keep the total doping amount fixed at 10%, and we are just changing the relative concentration between the R811 and the S811. But okay, but this number here, this X here, the percentage of R811 basically translates into a value of the cholesteric peak. So basically, if you are capable of predicting the percentage of X in these two samples, we are more or less predicting what is the cholesteric peak in the cholesteric phase. And we will try to do that using our ordinal networks. And because now we are working with the real world, we are working with experiments, we first ask if these ordinal networks are capable of identifying phase transition in these materials. And also in this case, we have, in additional to first order transitions, we also have second order transitions that tend to be harder to differentiate just looking into the textures. And what I'm showing here is an example of transitioning of an 8CB sample doped just with R811. So we are seeing a transition from the chiral SMACTA to the cholesteric phase. And we know from the literature that that's the critical temperature. So in this particular temperature, we would expect to see our system to change from the chiral SMACTA to the cholesteric phase. But again, you can see that it's very hard to differentiate these textures. But we can ask if our ordinal networks can do that. So we map these textures into an ordinal network using embedding dimensions dx and dy equals 2. So we have 4 values. So because of that, we have 24 nodes in this representation, these network representations. And again, just to illustrate, we estimate the average shortest path. I'm actually only showing the average shortest path, but another quantities are equally good. So if you estimate, for instance, the Gini index associated with the edge of this network, it will be it will be also capable of detecting the phase transition, exactly as we are seeing for the average shortest path. So what we see here is an abrupt change in this quantity as a function of the temperature, exactly around that took place around the critical temperature of the transition between the charismatic and the cholesteric phase. And I'm showing here just an example, but the same approach works quite well with other textures in our samples, in our experiments. Okay, but as a first application of machine learning with these ordinal networks, we have tried to predict the order of the phase transition. So for that, we select some textures around the phase transition, and we tag these textures as textures around the phase transition of first order or second order. And our goal will be to select a new image that were never exposed to the algorithm and say if that transition is from if that texture is from a transition of first order or second order. And to do so, we map these textures into the ordinal network. And this time, instead of using just the average weighted shortest path or any other metric, we actually use all edges of the network to train our KNN model. So in this case, we have a lot of edges, and all these will be used as features to train our KNN model. And that turns out to work more or less well. So we have here now the confusion matrix of this classification text for predicting if a texture is of a first order transition or a second order transition. And as you can see, the diagonal elements are close to 1, indicating that we almost always make the correct prediction for the texture. And okay, so in another classification and a similar approach, we did a similar approach to predict the doping concentrations in our E7 samples. And as I told you before, we have two kinds of E7 samples. We have the group 1 that are only doped with R811, and we have the group 2 that are doped with racemic mixtures of R811 and S811. That's what I'm showing here. And the idea this time is to predict the doping concentration just from the texture. So we have, again, our texture. We map our texture into an ordinal network, and we use the ordinal network edges to train the KNN to predict the doping concentrations. So what I am showing here again is a confusion matrix for the two groups of E7 samples. And as you can see, the confusion matrix is almost diagonal, indicating that our approach is quite effective in classifying or in determining the doping concentration directly from images of these materials. And in a final application, we actually tried to predict the sample temperature. So we get now a regression task, where the goal is to predict the sample temperature using just the texture. And the approach will be more or less the same. So we have texture that will be mapped into an ordinal network, and we get all edges to train our KNN that will output this time the temperature of the sample. And as you can see here, I'm showing just the results for the E7 samples. So the two groups of E7 samples, those doped with just doped with the R811. We have, I'm showing here the association between the predicted and the true temperature. And so in case we have a perfect regression, this will be just a straight line. And as you can see, it's not the case. We have a lot of noise, but even so, the coefficient of determination is somehow large. So we have a coefficient of determination that is 0.89 for this group of samples. And for the racemic mixtures, it actually works somehow better. So we have a coefficient of determination that is equal to 0.96 for this group of samples. And basically that's all. So that's what I have prepared to talk today. So I think that we can say that we have demonstrated that these ordinal methods, in particular the complexity entropy plane and the ordinal networks, are quite effective in extracting features from liquid crystals. And perhaps we can be sure about saying that because we have used these features with one of the most simplest machine learning approach, and that turns out to predict properties of liquid crystals with good accuracies. Okay, so perhaps if you got interested in using these ordinal methods, we have recently released a Python module that implements a lot of these methods, that is the OrdPy. So if you use Python, you can just do pip install OrdPy. And there is also a paper that describes the functionalities of these modules. And to finish, I need to say thank you to my collaborators. So most of the work you have seen was done by Igor and Arthur. They are PhD students working with me. And the part of the liquid crystals, the simulations, and the experimental analysis was performed by Professor Rafael Zola, who is our collaborator in these studies. And I also need to say thank you to Matthias Perk for working with us in developing these ordinal approaches. So there are these two papers. This one is not available yet, but we have a draft. So in case you mail me, I can send a copy. Actually, it was just accepted in chaos, solitons, and fractals. So I guess it will be that there will be an online version soon. And that's it. So thank you very much for your attention. I hope you could understand my bad English.
Oh, thank you. Very nice, Haroldo. It was very didactic and very interesting. So those who have questions can unmute and ask.
Okay, I have one question. Rodrigo, maybe, yes, thanks. Okay, so thank you, Haroldo. It was a really nice talk. So I have a really simple question. So do you hear me?
Yeah, I am.
Okay. So I don't know if I really understood the definition of complexity, because I see that the complexity, if I understood correct, is this D times H, okay?
Yeah, times the disequilibrium times the normalized entropy.
So when I saw this, I thought, okay, I have a one-by-one relation between complexity and entropy. So I suspect that, okay, I would gain nothing to look to complexity, to the complexity plane against the normalized entropy. But when you plot this, you see that there is a whole range of possible values for the C and H. So then I suspect that the disequilibrium inside of it have something related with the entropy as well. Because just by looking to the definition of disequilibrium, you can see this. But why not just make the analysis with the map of disequilibrium against normalized entropy? It would not be the same result?
Yeah, I guess if you just use the D, I think that will be more or less the same. But I think that the reason why we have for instance, for a given value of entropy, we have a range of possible values of C. It's exactly because the value of D depends on two distributions. So it depends on the P, that is the system distribution, but it also depends on the uniform distribution in this form here. But I think that you are right. I think that we will have basically the same results if you just use the disequilibrium. But the idea here, it was just to apply this approach that is somehow a well-known approach. So we have this complexity entropy plane. And also because the complexity has these, I think that it's a good, this intuitive meaning for complexity. So, but let's say from the more practical usage, it's totally fine. I think that we can just use the values of D and the values of entropy. It will be probably, it will not lead to different results. It will be basically the same. Actually, one thing that perhaps you can also use is just the ordinal probability distributions. So we can use these as the input for training the algorithms. And because we do not need to make a summary of this distribution, we can use all the values of the probability. And we actually did this in some tries here, and it works also very good. Just using the ordinal probability distribution. That is somehow more or less what we did with the ordinal network. So instead of calculating properties of the ordinal network, we use the structure. So we use all the edge weights of the network as features of the image.
Okay, thank you.
Thank you.
So, who else has questions?
I have a question.
Please.
So in your Haroldo, in your the transition from nematic to isotropic, when you see the plot of the entropy and the complexity as a function of the reduced temperature, the error of the entropy and the complexity decrease a lot on the peak, right, on the peak region. So it should be.
So you mean the bands here? So
On the error bars. So
yeah.
So it should not, I don't know, you have fluctuations of the order of the system, and so you should not increase
if you think about this idea that in the transition we have these large fluctuations, deviations, I think that we should have large deviations here, but it's actually the opposite. I haven't thought about this. So we have actually what we have is that the standard, this is actually one standard deviation of the value of the entropy. And perhaps what we see is a decreasing of this quantity as we approach the critical temperature, but I don't know why actually. But well, at least I think that we can say that these images very close to the critical transition. I don't know why, but they probably are more similar at least in the sense of the values of entropy and complexity. And that's, yeah.
Okay.
Thank you. More questions?
Okay, I have another one. If no one,
yeah.
Does anyone
go ahead?
No. Okay, so I can make another one. Okay, so it's just about this permutation entropy.
Okay.
It's more a curiosity, maybe. I know that things get tricky when you have time series that are not, that they have a trend. See, they are not stationary. I suppose that with this whole permutation entropy, the same problem would appear as well. So because this probability will not be correctly estimated if you have some trend in the time series. Is it clear what I mean?
Yeah, I think that, well, for instance, in the case of the Hurst exponent, so the fractional Brownian motion, it's not stationary. So in this particular example, we have a time series that is not stationary. But if we estimate the values of the ordinal probability distribution, it converges to a given value. So that's, let's say, the non-stationarity is not a problem for estimating the values of entropy and complexity, I guess. So yeah. Even if we have a time series that's non-stationary, we can still estimate the values of entropy and complexity. And yeah, okay. Actually, that's I think that's a good feature of the model, because we are just looking into very localized trends. And by doing so, we do not need, I don't know, maybe I think that you are thinking about perhaps the trended fluctuation analysis, yes, that remove these trends. But in this case, I think that these trends informs about the features of the time series. So okay. if we have let's say, a down, like here, an upward trend, so this will translate into a probability distribution that has the probability associated with the 0, 1, 2 will be very large. So I think that that's not a problem. That's just a feature of the approach. So it will be telling you that this ordinal pattern indicates that your time series has this trend. So a strong trend to increase.
Okay. 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 Thank you.
Thank you.
Questions? Oh, Not to have a very naive question, if you don't mind. I like this application to predict not to calculate the properties of the liquid crystal, because it avoids complicated experiments. Just by looking at the image, you can predict the pitch and other properties of the liquid crystal, the other parameter. But do you think these models could be trained also to provide the time evolution of a dynamic liquid crystal, like if you have or an active liquid crystal, or something that's not completely relaxed?
Yeah, that's one thing that I actually do not know. But well, if one thing that we are actually trying to do here is what, I don't remember the name. So I think that it's electroconductivity. So when we apply when you apply I think that is an electric field that has some periodicity, and in this case you find not a how can I say, you find a dynamic texture. So in this case, and our idea in this case is to look into phases in these materials by estimating the values of entropy and complexity, and probably by doing some clustering. So, but well, just for predicting the evolution, I don't know. I think that is probably too much for two values.
Okay. And I don't know, another naive question. How do you choose the number of nodes in this ordinary network to avoid overfitting?
The number of nodes is actually the number of permutations that appear in the representation of the image or in the representation of the time series, then the number of unique permutations. So in this particular example here, you have 5 permutation symbols, but you have 2 of the type 0 through 1. And so we have 4 unique permutation, and that's why we have an ordinal network with just 4 nodes. But in more general, the number of possible nodes in our ordinal network is also equal to the number of possible permutations that will be for time series. It will be the log of it will be the embedding dimension factorial, and for image it will be the product of the embedding dimension factorial.
Thank you. More questions? If not, we can finish this presentation. So thank you very much, Haroldo. We'll stop the recording now.
Thank you for the invitation.